Welcome back, everyone. The last couple of videos have been all about antiderivatives, families of antiderivatives, and indefinite integrals. And in this video, we're going to talk about how we can visualize some of these antiderivatives by graphing them. Now, we can't graph families of antiderivatives because if I have a function plus c, I have no way of graphing that without knowing what c is. But as we saw in the last video, if we're given some kind of initial condition, we can use that to find precisely what c is, and then we have one specific function, and then of course we can graph that function because we know what it is now. And so more specifically in this video, we're going to be starting with the graph of a function, and then trying to graph the antiderivative of that function given some initial condition. So let's say I have the function here in red, and I want to find its antiderivative. And in finding the antiderivative, we're saying that the red function is the derivative of whatever we're going to find. So this is the reverse of what we were doing earlier on in the term. Early in the term, we started with a function and tried to graph its derivative, but now we're starting with a function that could represent the derivative of what we're trying to graph. And let's say that the function in red is f prime, and we're looking for f. Now I could have also started with the function f and said that we're looking for capital F, which is the antiderivative. It's the same thing. Just whatever function you start with, we're trying to find its antiderivative. But I think starting with the idea that this is the derivative function, trying to find the original function, will help you think through it a little bit easier. But before I can actually graph the antiderivative, I have to be given some kind of initial condition, because as we know, a function can have many antiderivatives. And so let's say that the initial condition I have is that f of 0 is equal to 0. And so I know that one point on my function is 0, 0. So let's go ahead and pencil that in. And from here, I'm going to try to give a rough sketch of the original function by keeping in mind that the function in red is the derivative of what I'm trying to find. And so the value of this derivative function represents the slope of the original function at any point. For example, from x equal to 0 to x equals 2, the value of the derivative function is 1. And what that means is that over that interval, the original function has a slope of 1 because the derivative represents the slope of the function. And I can very easily draw a line with a slope of 1. Now after 2, the function begins to decrease. However, it's still positive all the way from 2 to 4. And the fact that the derivative is still positive means that the original function should be increasing over that entire interval. However, it's going to be less steep as the derivative function begins to approach a value of 0. So let's continue to sketch the antiderivative, and we're going to show that it is an increasing function on that interval, but it is increasing less and less as it gets closer to 4. Because once again, the derivative is getting closer to 0, and when the derivative is 0, the function is going to have a horizontal tangent line. And then after 4, the derivative function goes negative. And so if the derivative is negative, the original function is going to be decreasing on the interval. And so let's draw a function that is decreasing after 4. And so this function here in black represents the antiderivative of the function in red with an initial condition that f of 0 is equal to 0. And now when you're doing this, it does not need to be quite so perfect. There's just no way we could expect that from you. Now, some things that should be perfect is if you're given an initial condition like f of 0 is equal to 0, you should draw an antiderivative that goes through the point 0, 0. And if the derivative function is constant, it's very reasonable to ask you to draw an antiderivative that has a constant slope there, like this function did from 0 to 2. Now after 2, if it's not quite that nice, it's fine. It's just going to have the rough sketch. Now we can check our work here by using the tools from earlier on in the term, and by starting with the function in black, we can ask ourselves if the derivative of that function is the function in red. Well, from 0 to 2, the function in black has a constant slope of 1. And so the derivative should have a constant value of 1 over that same interval, which it does. And then after 2, the function is still increasing, but we can see it's increasing less and less all the way up to 4. And so the derivative function should always be positive over that interval, but it should be trending towards 0, which it does. And then after 4, the function begins to decrease, and so my derivative function should be negative, which it is. So that's one way to verify your work if you're more comfortable with derivatives than you are with antiderivatives. And something else you might notice in this problem is that the derivative function when x is equal to 2 is not differentiable because it has a sharp corner there. However, we were able to draw a perfectly differentiable and continuous antiderivative. And that's because when finding an antiderivative, you don't need to be differentiable. You just need to be continuous to guarantee the existence of an antiderivative. And so in a sense, it's easier for a function to have an antiderivative than it is to have a derivative, because the function only needs to be continuous, not necessarily differentiable as well. And even then, there are plenty of functions that are not continuous that still have antiderivatives. It's just that when it is continuous, it's guaranteed to have an antiderivative. So let's do one more example that's maybe not quite so nice. And we're going to start with the function here in red and try to graph its antiderivative. And we're going to use the initial condition here that f of 0 is equal to 1. And I want to make a point that the initial condition has to be given to you. It's not something that you come up with on your own. You would see it in the problem if it's relevant to the problem. But with that initial condition, we know that we have at least 1 point on this antiderivative that is very specific at 0, 1. So let's go ahead and pencil that point in. And from there, I like to look at which segments of this derivative are positive and which segments are negative. And this derivative is positive from 0 to 2. And this being the derivative function, I know that the original function has to be increasing over that entire interval. Now over that interval, I see that the derivative function is the largest, a little bit before when x is equal to 1, and it's the smallest right around when x is equal to 0 and 2. And to reflect that in my antiderivative, I know that the antiderivative will be steepest right around x equal to 1, and it'll be less steep around 0 and 2. And that's what I've drawn here. I started at 0, 1, it is increasing over that entire interval, but it is increasing the most steep a little bit before 1. Now all the way from 2 up to 5, the derivative function is negative over that entire interval. So the original function will be decreasing over that same interval. And much like before, I can look for where this derivative function is the most negative, and that looks to be right around when x is equal to 3.75. And so my original function is going to be the steepest right around there. But with that in mind, I can draw a function that is decreasing over that entire interval, because once again, the derivative is negative over that entire interval, and it is the steepest slope, the steepest negative slope, right around 3 3/4. And then right around when x is equal to 2 or x is equal to 5, the slope is closer to 0 because the derivative is 0 at those points. I just want to stress again that your graph does not need to be this perfect. It just needs to have all of the same main characteristics of where it's increasing where it's supposed to be, it's decreasing where it's supposed to be, it has a horizontal tangent line where it should, and it roughly reflects the steepness as given by the derivative function. And finally, it should have that 1 point, that initial condition should always be there.